All right, so let's talk about this average, weighted average that happens with elements. So if I had a class and these were the average ages of this, or these were the ages of the individual students, right? So I had four kids who were 15 and a bunch of kids who were 16 and one kid who was 17. The way you would take the average of this class is you would just add up all these ages and divide by the number of students, which was 14. And so 221, which is what all these numbers are added up, divided by 14 gives you an average age of 15.785, which is great. It's a great way to do it. I'm going to show you a different way to do this. There's another way, and that is determining the percentage that each of these things are and applying that with their ages. So this one here, the 15, it turns out 4 divided by 14 is 28.57% of this class is 15. And then 64.29% of the class is the age of 16, which is this 9 students divided by 14. That's how I get that number. And then 1 student out of 14 is 7.14% of that class. So hopefully at some point you've seen how you can turn a percentage into a decimal by moving that decimal over 2 places, 1, 2. So 0.2857 is 28.57%, and 0.6429 is 64.29%, and 0.0714 is 7.14%. So when you're turning percentages into decimals, you just move the decimal over 2 places. All right, then you take that decimal representation of the percentage and multiply it by the age, and you get another number. So you do that for each of the ages, and then when you add this, look, it's the same number. It works just as well. Now, the reason I'm showing you this is because when we are doing atoms, and we're talking about billions upon billions upon billions of atoms, like neon 20 is all these sort of atoms, right? 90% of all neon is neon 20, has 10 protons and 10 neutrons. 0.3% is neon 21, just a fraction of all neon is neon 21, 0.3%. And then the rest is neon 22. So neon with 10 protons and 12 neutrons, neon 22 consists or makes up 9.2% of all neon. Using the addition method that that's going to take forever. Then billions upon billions of atom and having to add 20 plus 20 plus 20 plus 20 plus 20, over and over and over again. It's not very efficient. So what is efficient is using this percentage thing, because people can figure out this percentage thing, and I'll show you how here in a minute. So we know that 90.5% of all the neon is neon 20, and 0.3% of all the neon is neon 21, and 9.2% of all neon is neon 22. So we take that percentage represented as a decimal by moving the decimal over 2 places. So 0.905 times the mass, 20, gives us a number, 18.1. And then we do it again with 0.3. So we move the decimal 2 places, we multiply it by the mass, and we get 0.06. 9.2%, we move the decimal 2 places to represent the percentage as a decimal, multiply that by the mass, and we get another thing. And then when we add all those up, we get what the weight or the mass of neon is on the periodic table. That's how we get this weighted average on the periodic table. And we did a lab with this using BBs, and some were metal and some were plastic. And if you mixed up the different ratios, you got different numbers. So here it was. So the metal BBs had a 0.345 gram mass each, and the plastic ones had a 0.111 gram each. So if you had a 50-50 mixture representing 50% as a decimal would be 0.5. So you would say 0.5 times the mass of one BB plus 0.5 times the mass of one plastic BB. Add those up and you get what the average mass, if you had a 50-50 mixture of BBs, what the average mass of one of the items in there would be. And then if you did 75% metal and 25% plastic, somewhat not surprisingly, when you get your answer, it's leaning more toward the 0.35. It's closer to that number than it is to the plastic BBs because of the mixture. The majority of it is metal, right? 75% or 0.75 times this was metal. So this number leans more toward the metal BBs than this number because it was 25%. And if you did it the other way, where it was 75% plastic and 25% metal, the average weight would be closer to the plastic ones. Okay, so the bottom line for all this is average atomic mass is the weighted average of atomic masses of naturally occurring isotopes. And the formula is you're going to take the percent of some isotope, multiply it by the mass, and then add it to the percent of the other isotope times its mass. And so here's some examples. Chlorine has two principal stable isotopes, chlorine 35 and chlorine 37. We know that 75.78% of all chlorine is chlorine 35, and that 24.22% is chlorine 37. So if we want to see what's on the periodic table for chlorine, what we do is we do this math we were just doing. We convert this percentage to 75.78 into a decimal by moving the decimal over two places. So it's 0.7578. Multiply that by the mass of chlorine 35. And then we take this one and move the decimal over twice. So 0.2422. Multiply that by the mass of chlorine 37, which is 37. And when we multiply these two numbers, we get 26.52. These two numbers, this is order of operation stuff, 8.96. So then we've multiplied, all that's left is addition. So we add those two things up. And that's about what it is on the periodic table. And if you look on what's called a mass spectrum, which is something we used to run at work, you will see that when this instrument takes a measurement of chlorine, it's going to show a relative abundance of chlorine 35 to chlorine 37 as a 3-to-1, right? So this peak is about 3 times the height of that peak because there's 3 times as many 35s as there is 37s. All right. I don't know if you really wanted to know all that, but there it is. So hopefully you can do that as well for your test, and that's that.